Today, we're going to be discussing a problem on how to find the rate constant given the information in the example, which reads as consider this first-order reaction. Given the frequency factor and activation energy for the reaction are 3.98 times 10 to the 13th seconds to -1 and 161 kilojoules per mole, respectively, calculate the rate constant at 600 degrees Celsius. Now you see, there are a lot of ways to calculate the rate constant, but given the information in the problem, that leads us to one particular formula, known as the Arrhenius equation. Let's take a closer look at the Arrhenius equation. We can see that it's K, the rate constant, is equal to capital A, which stands for the frequency factor, times mathematical quantity E, raised to the negative power of energy of activation over gas constant times temperature. Now let's look back at the information we're given and see what we have and how we can plug that in. We're told frequency factor, which corresponds to 3.98 times 10 to the 13 seconds to the power of -1, and 161 kilojoules per mole, which corresponds to the activation energy. And we're given a final piece of information that this temperature is at 600 degrees Celsius. Now let's see if that's enough information to solve our problem. Breaking down this equation, we can see that K is we put a question mark, that's what we're trying to find. Frequency factor A is 3.98 times 10 to the 13th seconds to the power of -1. Energy of activation is 101 kilojoules per mole. Except wait, there's a little bit of a trick in here. We have our gas constant, which, as the name implies, is constant, and it's in units of joules per mole times kilogram, and we're given kilojoules. But that's a pretty quick fix. We can change units, so 1 kilojoule is equal to 1,000 joules, so we can cross those out, and we're left with 161,000 joules per mole. And there we go, we're in correct units, and we can move on. Like I said, our gas constant is 8.314 joules per mole times Kelvin. Our temperature, which is given in 600 degrees Celsius, has the same problem as our energy of activation. But again, that's a pretty quick fix. By adding the quantity 273.15, we convert this to the correct unit, 873.15 Kelvin. Now from here on out, we just plug in and we see what we get. So we have K equals frequency factor 3.98 times 10 to the 13th seconds to the power of -1 times mathematical quantity E raised to the negative, don't forget that negative, 161,000 joules per mole over 8.314, our gas constant, times our temperature corrected to Kelvin, 873.15. And as we can see, the moles cancel out, the moles, joules, and Kelvin cancel out. So we're left with the rate constant of 9.29 times 10 to the 3rd seconds to the power of -1, which again, as a quick way to check, is the correct units for a first order reaction. And that is how we use the information via the Arrhenius equation to solve for a rate constant.